this is going on page 136 when we're done. This is our introduction into sequences. We're going to spend some time on sequences and series of numbers. Oh, shoot, hang on. Doing weird things here. So let's have the definition of a sequence first. It is a set of numbers with a particular order or position. Oh, not an or position, I'm sorry. I can't read that far and I wanted to make sure. I know, this is why we weren't writing that fast anyway. Or pattern. Pattern is what I meant. Sorry, I've been writing position in the other class all day. No position. Just, well, order and pattern position, even the position is not necessarily wrong, it's just not what I meant to write. Order or pattern, and then each number is a term. Okay, so we have terms, and each number is a different term. So there's different types of sequences. We have finite sequences and infinite sequences. Okay, so we know what infinite means, right? Goes on forever. So finite is the opposite of infinite, means it doesn't go on forever. So a finite is a sequence with a limited number of terms. Means we could actually count them, right? So one example would be just the set. It would be like 1, 2, 3, 4, 5. So then an infinite sequence is a sequence with an unlimited number of terms. So this one could be 1, 2, 3, 4, 5, 6, 7, comma, dot, dot, dot. And then that would be like the set of whole numbers. So you just continue on into infinity there. So finite and infinite. So our term notation, this has a lot of different notation. It's not necessarily complicated. You just got to pay attention to what's what and think about it. So the first term in a sequence is denoted with a sub 1, because it's the first one. And then each subsequent term is denoted as a sub n plus 1, right? Where n plus 1 is the term number in the sequence. So here's how this works. It does not matter what the numbers in the sequence actually are. This is the first term, so this is a sub 1, it's 2. A sub 5 is going to be the fifth term. 1, 2, 3, 4, 5, that's 14. Okay. Now that's all that we have there, so let's continue this pattern. What's happening here in each number? We're adding 3, so it's going to be 17, and then 20, and 23, and 26, 29, 32, 35, 38, 41. Yeah. Okay, turn that off, please. What? Can't you just multiply what? What is that noise? Oh, that was like Is this 14 by 3? Is this 14 times 3? So 14 times 3 is 52. No, it's 42. Sorry, it's 42. Duh. Okay, so could you come up with a pattern? Yes, you could. You don't have to write them all out. So basically, I think what you're asking is, could you come up with a pattern so that you don't have to write them all out? Absolutely. You can come up with a little equation, and we're going to do that. So yes, that absolutely works. But I just wrote them all out because I wasn't there yet. That's fine. So this is term 5. So this is 6, 7, 8. So this is 23. And then term 14 is 41. But it's not just 14 times 3. So just make sure we understand that. Like we'd have to come up with what the little pattern is, which you've done patterning like that before, and it's not that big of a deal. We'll talk about how to do that in just a minute. All right, so then let's talk about some other of the vocabulary here. We've got sequences. So it says since each term value is paired with exactly one term number, a sequence is a function with the following properties. The domain is the set of term numbers. Oh, I've got to spell term correctly though. Term numbers. Okay, so 1, 2, 3, 4, 5, it's always 1, 2, 3, 4, 5. Like that doesn't change. The actual values, so this is the term values, that is my range. Okay, so the domain is the term numbers, the range is the term values. Domain will always be 1, 2, 3, 4, 5 to wherever it stops or infinity. The range will be whatever is appropriate for that problem. So in an infinite set, the domain is the set of natural numbers. Which is your 1, 2, 3, 4, 5, all of them. Okay. So there's a couple different ways to write the rules for these, which y'all were kind of trying to do on that other one there. One of them is what's called a recursive formula, and these are a little bit easier. This is just a rule in which, I know there's a lot of writing today, but you need these definitions, in which one or more previous terms are used to generate the next term. Okay. A rule in which one or more previous terms is used to generate the next term. Okay, that's how we said like we're just adding 3 every time or whatever. So if we have what's called the Fibonacci sequence, it looks like this. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so forth and so on. So in this sequence, a sub 1 is 0 because that's the first term, right? A sub 2 is 1. Then how do we get each of the next terms? What do we do? So to get this term, I take the previous number and do what?
Add it to another previous
the one before that, right? So I have to add the 2 previous ones together. Does that make sense? So that means to get a sub n, whatever n might be, I have to take the number before it, which would be a sub n minus 1, and to that I add a what? Sub n minus 2. That would give me my 2 previous terms. So it's called a recursive formula. You get the first 2, or the first term, sometimes the first 2 terms, and then you go from there. That's basically saying you add the 2 terms before to get the next one. But to get the 50th term, you have to know term 49 and 48, right? So it's still, you have to write a whole lot out, but that's at least explaining the pattern. Okay, one way to do that. So then we're going to give, we're going to give the first 5 terms in the sequence. So notice here it says n has to be greater than or equal to 2 because we start with that 1 right there. So we have a sub n equals a sub n minus 1. That means the term before it minus 7. So when I do this, I know my first term, it's 25. To get a sub n, or which is 2, what's 2 minus 1? 1. So a sub 1, which is 25, minus 7. What's 25 minus 7? 18. And then I subtract 7 from that, and I get 11. I subtract 7 from that, and I get 4. Almost worth it. I know, I was worth it. And then when I subtract 7 from that, I get negative 3. Those are my first 5 terms. That means this only works if I'm looking for n that's greater than or equal to 2. This is right here, n equals 1. n equals 2, n equals 3, right? Does that make sense? N equals 4. The n value is 1, 2, 3, 4, and 5. So I have one, they gave it to me. This rule only works if you're looking for an n that's 2 or greater. Okay, yeah. Well, no, because they only asked me for the first 5 terms, so this is a finite set. No, these are the natural numbers. Yeah, the domain, not the range. Okay, we good? All right, let's do number. Let's jump over to number. Well, let's go ahead and do number 2. Then we'll just jump to one on the back. So here, I have a sub 1 is negative 2. So then to find the next one, I have to do 3 times this. So 3 times negative 2 is negative 6, plus 1 is negative 5. Take negative 5, multiply it by 3. I get negative 15, plus 1 is negative 14. 3 times a negative 14, negative 42, plus 1 is negative 41. So negative 41 times 3, negative 123, and then I add 1 and I get negative 122. Okay, so do you understand how the recursive works? We good? Easy enough? All right. Let's do, actually, we are going to do 3 and 4 just because they kind of show up a little bit differently here. Again, we want the first 5 terms, right? So I want, this is a sub n, we'll give, so I know what 1 is, it's 40. Then I have, this is a sub n minus 1 and n minus 1, which means I'm using the same number in both. If I want the second term, that means I'm going to do 1/2 times a sub 1, which is 40, plus 40, right? So half of 40 is 20, plus 40 is 60. Then I use 60. Half of 60 is 30, plus 60 is 90. Then I do half of 90, which is 45, plus 90 is 135. Then I do half of 135, which is 77.5. Okay, and then I add that to 135. Is that right? Okay, and then yes, 135 over 2. And then add that to 135. Well, that's fine. Add it to 135. And even as a fraction, you can put that in here. It doesn't say it has to be a decimal, right? But if you want the decimal, then what do? The SD. Yes. Yeah, so it's 202.5. But even the fraction would be fine there. Okay. Or 405 over 2. All right, we good? Let's look at number 4. Notice number 4, it gives us a sub 1 and a sub 2. And then it has a sub n minus 1 over a sub n minus 2. That means the 1 before it and the 1, 2 before it. So I have the first 2 terms. They are 8 and 10, right? And then to get the next one, I put, do I put 10 over 8 or 8 over 10? I put 10 over 8. Because look, y'all aren't even paying attention. Listen. When n equals 3, that means this is going to be a sub 2 over a sub 1, right? This is 1, this is 2. So I put 10 over 8. That gives me 5/4. Yes? Then to do the next one, I have to put 5/4 over 10. Are we capable of that? Yes, we put 5/4 over 10. I would put 10 over 1, right? Multiply by the reciprocal. 5/4 times 1/10. 1/8. Good. Good. Then you find the last one. You're going to put 1/8 over 5/4, right? Which is not nearly as scary as you make it out to be. Did I get 1/10? We good? So now we're going to take a pattern, or a list, a sequence, and we're going to create a recursive formula. Not the one that you were trying to do earlier, but a recursive formula. So in order to do that, I have to define the first one. So a sub 1 equals 9, right? So how would you describe to me in words what's happening here in this pattern? You add 4 each time, right, to the one before it. So that means that a sub n is going to be equal to the term before it, which is a sub n minus 1 plus 4, when n is greater than or equal to 2. Okay. Does that make sense? Everybody understand where that came from? Because it only works when n is greater than or equal to 2, because we already have a, or n is 1. These are n. I have this one. It doesn't work if I want to get the first term. It only works for the second term and beyond, okay? But it does ask me for the 8th term, right? So this is 1, 2, 3, 4, 5. I need 6, 7, and 8. And so here, with the recursive formula, you just have to keep adding 4, right? So you get 29, then 33, then what? 37. So a sub 8 is 37. All right, so let's look at this next one. What do you think is happening here? Something with multiplication. No, that's good. I mean, I just got to recognize that. That's okay, and that's what has to happen sometimes. You're like, okay, no, that doesn't work, but I tried. What do you think's happening here? Try and do more than one thing. Okay, let me ask you this. What is 1 plus, what is it? Good. If I add 3 and 1, I get 4 times 2 is 8. 3 plus 8 is 11 times 2 is 22. Right? You see that? Guess what? I'm gonna show you a formula tomorrow that helps you build those things, and you don't have to just stare at it. But that works. Okay? Does that make sense? So we need 2 terms in order to do that, right? Not just a sub 1. So we have to define a sub 1 is 1 and a sub 2 is 3. That means this is only going to work when n is greater than or equal to 3, because we already have the first and second term, right? So what we can do, we can write this a couple of different ways, but a sub n, the way that Michael said it, is you're going to take the 2 terms before it and add them together. So that would be a sub n minus 1 plus a sub n minus 2. And then after you add them together, you multiply by 2. Does that make sense? You could have said, I multiply both of the terms before it by 2 and then add. We would just write it out differently. But that works. Okay, everybody okay with all that? I hope so. Okay, so then we have to find a sub 8, which means we have 1, 2, 3, 4, 5. We got to do 6, 7, and 8. So y'all see if you can find the 8th term. You can even use your calculator. That's why I had you get it, just so all this stuff would be a little bit easier. Why do you think that? It's a big number. No, but you're kind of close. Yes, good. Tony, you got that? Wake him up. 1224. Okay. We good? What questions do you have? All right. So here's what I want to make sure you understand. These are called recursive formulas. Those n's are subscripts, right? It's the more kind of wacky way to do it, okay, but it works. So now we're going to talk about explicit formulas that look more like equations that you are used to, right? So an explicit formula is a rule in which the nth term is defined as a function of n. And this is what y'all were trying to do on that first one, come up with something plus 1 or whatever. And that work, but it's got to work for every n and not just like the one before it. And that's what these are. So we're going to do some of these. We don't need to do every single one of these here. But it says give the first 5 terms in each sequence. So here's what I want you to remember when you're doing this. That they're asking me for the first 5 terms. 1, 2, 3, 4, 5. So the term numbers are 1, 2, 3, 4, and 5. That's the term number, okay? So to find each term, you just literally substitute in n, because these are all n's, right? So I substitute in 1. 1 times 5 is 5 plus 1 is 6. So to get the second term, I substitute in 2. 2 times 5 is 10 plus 1 is 11. Then I substitute in 3. 3 times 5 is 15 plus 1. Then I substitute in 4, and I get 21. Then I substitute in 5, and I get 26. It is just like add 5. But guess what? If I want the 38th term, I don't have to keep adding 5. I can just substitute in 38 and get my number. Does that make sense to you? This is what you were trying to do. And that's why this sometimes is better, depending on what you want. But here's what here's what you want to pay attention to. It is just like adding 5, right? But if I ask you for the 5th term, you can't just say, oh, I'm just going to multiply it by 5 or whatever, because that whole n plus 1 thing. But since this is plus 5, plus 5, plus 5, notice that that matches that number right there. Okay, that's going to help you write them in just a little bit, all right?
So would n of 0 be 1?
It's always greater than 0. Always starts at 1. On the front, the first term is always a sub 1. All right, so let's look at this right here. We're going to find these first 5. Okay, so I need 5 terms, right? So when I find my first term, and here I'm going to, I'm going to write out the 1, 2, 3, 4, 5 again, but I'm not going to do that every time because you don't have to do it every time, but 1, 2, 3, 4, 5. Right? So I substitute in 1, right? This is going to be 3/2 to the n minus 1 power. So 1 minus 1 is what? 0. What is anything to the 0 power? No. 1. Anything to the 0 power is 1. Then I substitute in 2. 2 minus 1 is 1. Anything to the first power is itself, so this is just 3/2. Then I substitute in 3. That's going to give me 3/2 squared, which is what? 9/4. You just square the top and square the bottom. Then when I substitute in 4, I'm going to get it to the 3rd power, which 3 to the 3rd power is what? 27 over 8. Then when I substitute in 5, I get 3/2 to the 4th power. Well, taking something to the 4th power is just squaring it and squaring it again, right? Wasn't this that squared? So you get 81 over 16. Everybody okay with that? Any questions at all? All right. Yeah, we're going to write a couple today, just kind of by intuitively figuring it out. But then I'm going to give you a formula that we're actually going to use that's going to make that easier as well. Okay. All right. Do we need to substitute any more in, or y'all got it? Yeah, you got it. All right. So now it says write now, and pay attention to the terminology. Explicit, not recursive. Okay. Explicit rule for each sequence. Then find a sub 25. Oh my gosh, I know. So here's what we want to look at. You start by looking at the differences here. This difference is what? 3. And then this difference is 5, and then this difference is 7, and then this difference is 9. So it's not really as pretty as we would like it to be able to come up with something, right? But instead of trying to force it into an equation like that, do those look like a set of anything you recognize? They are odd. Are they odd numbers? They're not all odd numbers. Is that what you said? Oh, the differences are all odd numbers, yes. Okay, I was like, they're not odd numbers. Is it the one before it's squared? But look at this. No, okay. I should have said that. I'm sorry. Once that isn't anything pretty, then I don't want you looking at that anymore. I understand what you're saying. So how would you describe this set of numbers? Yeah. And this is the term number 1, 2, 3, 4, 5. So it's not even anything fancy, right? So a sub n is equal to n squared. It's that easy. So a sub 25, which is what it asked me for, was 25 squared. Wait, Tony knows it because he practiced. 625, good. Because he practices perfect squares because I told him to. Is that right? 676. That's okay. You're close. All right. So now let's look at this one. Look at this. What's the differences here? 2, 2, 2, right? And remember how I showed you up here? These differences match that number right there. So that means that this is going to be a sub n equals 2n something, right? So if I'm going to look at this, right? If the term number is 1, 2 times 1 is 2. What do I have to add to that? 7. And so then you can test that out for the second one. 2 times 2 is 4 plus 7 is 11. 2 times 3 is 6 plus 7 is 13. Okay, does that make sense? Look at your differences there. And this is your basically like your y-intercept is where you're starting. Why are you looking at me like that? Ask me a question. Did I totally lose you with the whole thing? All right. Did you understand how I got the 2? Everybody with the 2, yes? Okay. So then since I know that it's, the differences are 2, like this wasn't even, and these aren't even the differences. But remember, those didn't work like that, so I erased them. The differences are all 2, so it's going to be 2n plus or minus something, right? And so then when I know here, this is when n equals 1, 2, 3. So if I just look at that first term, if I do 2 times 1, that's 2. Then to get to 9, I have to add 7. That's where that 7 comes from. Does that make sense? And then you can test yourself in case you were making stuff up, right? Jump to the 1, 2, 3, 4th term. Here's the 4th one. 2 times 4 is 8, plus 7 is 15, and so it's working. Okay, does that make sense? And again, I'm going to give you a formula for it, but this is still, you've done, when you wrote equations in algebra and stuff, you did all that stuff. So when you want to do a sub 25, what's that going to be? 57. And we don't have to just keep adding 2 till we get there, right? That's one reason why you want to find those patterns there. Okay, we good? Any questions? All right, so on this next one, it says to write an explicit and a recursive formula for each sequence. I want to see if you can do that on here. Okay, explicit is what we just did. Recursive is the first thing we did. See if you can get those written. Okay, so you haven't defined what the rest of that recursive is. You don't have the whole answer. You still don't have the whole answer, and that wouldn't be right anyway. Go back and look at those examples. Good, and then you need to also have that part right there. Okay, but yeah. You don't have the whole, oh no, I'm sorry, yes you do, because this is all part of it. Yeah, yes, good. Good. How do you know where to start? Huh? Yes, that has to be defined, otherwise you don't know where to start. Oh, this one would have to be n is greater than or equal to 3 because we have 1 and 2 defined, so we have to start with 3. Here, since we have 1 defined, we have to start with 2. Okay. All right, so let's talk about recursive. For the recursive, you have to define the first one, at least the first one, sometimes the first and second. So I have a sub 1 equals 4. You got to know where you start. And then tell me in words what's happening here in this pattern. You're adding 3 to the one before it. So that means then I have a sub n is equal to a sub n minus 1 plus 3. Do we all agree with that? And since I had to define this first one, n has to be greater than or equal to 2. I can only start at 2. So this whole thing is my answer. Like all of it's important. If I leave off a sub 1, I don't know where to start. Make sense? So by doing that, I've already decided, okay, I'm adding 3 each time, right? So my explicit, which is just a sub n equals, it's going to be 3 times n, and then plus what? Plus 1. Why did I put a 2? Yes, because I have defined what a sub 1 is. So this does not help me find a sub 1 because this only works when you substitute in 2 or greater. I can't substitute in 1 because then I get a sub 0 and it doesn't make any sense. Yeah. A sub 2, 2 minus 1 is 1, and then so I take that a sub 1, which is 4, add 3, that's how I get 7. Does that make sense? We good on that? That's why up here, we had to, where was it? Right here, n is greater than or equal to 3 because we defined both of these, right? And so if I substitute in a sub 2 here, it's not going to make any sense because that's going to give me 0 as well. So once I defined both of those, I have to start at 3. Does that help? So however many you have to define to get it, the next one is the one where n starts. All right, so let's look at, and maybe sometimes the explicit's easier to figure out first than the recursive. It just depends. So tell me what's happening here in number 16. I'm adding 1/2, right? 1/2, 1/2, and so forth and so on, right? Which means that my explicit is going to be a sub n equals 1/2 n, and then what? Is that it? That's it. Because if I find the 1, 2, 3, 4th term, I substitute in 4. 4 times 1/2 is 2. Like, that's it, right? So then a sub 1 for my recursive is 1/2. And then a sub n is going to be a sub n minus 1 plus 1/2. Because I'm still adding 1/2. It's a different way to look at it. But this one, if I want the 50th term, I have to find all 50 terms. Where if I want the 50th term here, I don't. Okay. And then this would be n is greater than or equal to 2 again, because I had 1. Okay. All right, we good? Questions? You got this. What questions do you have? Anything? Don't be afraid to ask. You got this. Okay.